Welcome to this explainer. Today we're doing something a bit, well, unconventional. We are diving into the brilliant insights of sports medicine expert Dr. Christophe Delong to demystify the incredibly complex neuromechanics of spastic hypertonia. But we're going to look at it through a totally different lens, the physics of high-level sports. So let's jump right in because the parallels here between an elite athlete shattering a world record and a patient just fighting to move their arm, it's absolutely going to change how you look at the human body. Picture the perfect engineering of tension. That's what you're witnessing here. The vaulter is deliberately bending the composite material of the pole, taking all that running speed, right, the kinetic energy, and packing it into immense potential energy. They're stockpiling a colossal amount of force inside those carbon fibers, just waiting for that explosive, perfectly calculated release. They've mastered tension to elevate themselves. The pole literally becomes an extension of their body, a tool of pure performance.
But it does make you wonder, what on earth does an elite pole vaulter have in common with a neurological brain lesion? Seriously, what happens when our body's own internal spring system, that exact same capacity for elastic tension, completely breaks down? In a healthy system, we control this tension. But when the nervous system takes a hit, that very same tension transforms into a physical prison.
Which brings us to Section 1, the trap of spasticity, and the clasp knife phenomenon. Now, when a patient suffers a lesion in the brain's pyramidal system, say from a stroke or MS, the muscle basically loses its manager. The higher brain isn't regulating things anymore. And the result is wild. It's drastically different from Parkinsonian rigidity, which feels kind of like trying to bend a stubborn lead pipe. Spasticity is velocity dependent. Notice the pocket knife analogy. If a clinician tries to unfold a patient's arm, the faster they pull, the more aggressively that arm fights back, until suddenly, snap, it just gives away. That's the clasp knife effect in action. So what's causing that snap? Let's look at Section 2, the duel of the sensors. To really understand the snapping effect, we have to zoom way in and watch a literal microscopic duel happening inside the living tissue. It's a battle between two warring sensors. On one side, you have the muscle spindle. It's the aggressor here. When the muscle gets stretched, the spindle completely panics. Without the brain telling it to chill out, it demands an immediate, violent lockup of the limb. But over on the other side, hiding in the tendon, is the Golgi tendon organ. This is the protector. It senses that the tension is getting so crazy high that the muscle might literally tear itself right off the bone. So it slams the emergency stop button, forcing an instant release. And boom, the clasp knife snaps shut. Basically, this reflex arc just spirals totally out of control. It's a four-step cascade. First, the muscle stretches. Second, the spinal cord gets the distress signal. Third, the muscle violently contracts to protect itself. Now, normally step 4 is where the upper brain steps in, releases a calming neurotransmitter called GABA, and says, hey, relax. But with a pyramidal lesion, that calming signal never arrives. Those motor neurons become dangerously hyperexcitable, operating exactly like a hair trigger on a weapon. Okay, moving on to Section 3, mathematical modeling and differentiation. Let's look at the actual physics. Because spasticity isn't just a feeling, it's a cold, hard mechanical equation. This formula mathematically proves the whole core trait of the condition. The force of the resistance equals a reflex gain coefficient times the change in velocity times the stretch length. Do you see that velocity component right there in the middle? That is absolutely crucial. Spasticity relies on a critical velocity threshold. Cross that exact speed, and the muscle goes into a violent, nonlinear instability. In physics terms, we call this mechanical buckling. The system just completely overloads. If we actually put the vaulting pole and the spastic limb side by side, the contrast is mind-blowing. Yes, they both resist deformation, but look at what dominates them. For the pole, it's all about position. For the spastic muscle, it's 100% reliant on velocity. The pole is an elegant, deterministic spring built to give energy back to the athlete. The spastic muscle, on the other hand, acts like a completely busted, stochastically firing servo motor. It's trying so hard to protect the tissue, but doing it so clumsily that it just traps the patient. And that leads us directly to Section 4, complications and the Kinexa approach. Now that we've mapped out this crazy neuromechanical trap, we have to look at the harsh clinical reality. Just look at the tissue damage here. Spasticity is so much more than just a motor annoyance. If it's left untreated, this constant, unrelenting tension literally destroys the body structure from the inside out. A permanently locked limb creates immense, unyielding pressure on the skin and the surrounding tissues.
And these secondary complications cascade fast. We're talking tendon retractions where the tendon physically shrinks down in fibrosis, locking the joint so incredibly tight you can't even move it under anesthesia. Then you get deep, potentially life-threatening pressure sores because the locked joints strangle blood circulation to the skin. And underneath all of that, metabolically exhausting, round-the-clock chronic pain. Imagine having a severe muscle cramp that just never, ever stops.
But there is hope, and this brings us to the clinical solution pioneered by Dr. Christophe Delong, the Kinexa approach. In modern rehab spaces like this, the goal isn't just treating a disease. It's about diffusing that tension bomb before the initial motor failure triggers a total structural collapse of the patient's body.
The Kinexa approach hits the pathology systematically in 3 clear phases. Phase 1 is preventing retraction. This means prolonged positioning and stretching, literally fighting tooth and nail to maintain the muscle's physical length. Phase 2 is modulating the tension, which often involves chemically softening this rigid internal material using things like botulinum toxin. And finally, Phase 3, restoring functional movement. It's about turning that muscle back into an instrument instead of an immovable barrier.
So let's lock in our key takeaways from this explainer, because these numbers tell the whole story. First up, 100%. Spastic hypertonia is 100% defined by its velocity-dependent nature. Move the limb slowly, nothing happens. Move it fast, the trap snaps shut. The next number is 3. The diagnosis rests firmly on 3 distinct pillars. The velocity trigger we just talked about, the elastic recoil, where the limb fights to snap back like a loaded spring, and, of course, that unmistakable clasp knife snap, where it resists and then gives way. And 2, this entire mechanical breakdown is driven by that chaotic, microscopic duel between 2 primary sensors, the panic-stricken muscle spindles and the desperately protective Golgi tendon organs. We can map the physics, right? We can diagnose the muscles, and we can pinpoint the exact neurons. But ultimately, Dr. Delong's Kinexa approach reminds us of something profoundly human. Rehabilitation isn't just about unbending a locked pole. When someone's own body has acted as an unpredictable, violent prison, how do they ever dare to trust it enough to move again? If we can re-engineer the physics of the human body, what are the limits to how we can rewire the human mind to reclaim its own freedom?